Okay, so today we're going to be talking about another method for solving differential equations, and this is called separation of variables. And this is what we're going to be doing whenever we have two variables present, both x and y. So the method is basically that we want to separate the x's from the y's so that on one side of the equation we have all the x terms and dx's, the differentials, and then the other side of the equal sign will have the y's and the dy's. Then once we've got that, where x is with its differential and y is with its differential, then we can anti-differentiate. Once we've found this integral, this indefinite integral, then we'll factor out any GCFs we might have. And then after that, if we're given an initial value, so in other words, we're given some ordered pair that this equation has to satisfy, then at this step, before we solve for y, that's when we're going to substitute and solve for c. And then at the very end is when we're going to isolate so that we have y equals, and then we've got our equation. Okay, so let's try one. So here's kind of the classic separation of variables problem. I've got dy dx equals x over y. So my goal at first is that I want to get all of the x's and dx's on one side and y dy's on the other. So we can just multiply both sides of this equation by both of the denominators, or just think of it as cross multiplying. So if we cross multiply, I'm going to put the y's on the left side here so that I have y dy equals x dx. Okay, so we want an equation with y without all these differentials in there. So this is the part where we're going to anti-differentiate. So I'm going to have the indefinite integral of y dy, and forgive my iPad handwriting here, equals the indefinite integral of x dx. Okay, so I've got the indefinite integral of y dy equals indefinite integral of x dx. So now I can just apply the power rule. So I add 1 to the power, divide by the power, and normally this is where I would put plus c at the end. But because this is a differential equation and I've got these integrals happening on both sides, I'm just going to account for all of my constants over there with the x. Okay, so I'm just going to put equals and anti-differentiate on the right side and put the plus c over there with the x's. And again, that's also just taking into account the constants that would have occurred on the left side. It's kind of just like I'm making a shortcut and moving it over there, because a constant minus a constant is a constant. Okay, so this is that step that's kind of hard to catch sometimes if you haven't trained your eyes, but we've got a GCF here. Okay, so I'm just going to multiply the whole equation by 2 just to get rid of it, because if we don't do this, our answer is really not going to work. So we get y squared equals x squared, and 2 times a constant is some other constant. I know, it feels like you're just breaking all the rules of algebra, but it's totally kosher because it's arbitrary. It's not a variable. Okay, now this is the step here where if I were given some, ordered pair x and y for my initial value, I could substitute it here and solve for c. Okay, I don't have that on this problem, obviously, so I don't have to worry about that. All I'm trying to do, okay, our goal in solving these, G-O-A-L, oh my goodness, my handwriting is so bad on this iPad. My goal is that I want y equals something, right? So if I've got y squared and I want y, I take the square root. So I've got y equals square root of x squared plus c. And since I've reached my goal, I stop here. Okay? So not so bad. Let's try another one. Okay, so here we have dy dx equals 4xy. Okay, now I don't have a quotient. I can't cross multiply this time. So let's just take this one step at a time. I'll first move the dx over to the right side. So I'll multiply both sides by dx. So I get dy equals 4xy dx. Okay, and then I want to move y over so that it's with its buddy, the dy. So I'm just going to, since it's one big product, I'm just going to divide so that I'll have 1 over y dy equals 4x dx. Okay, so now that the y's are with the y's and the x's are with the x's, I have separated my variables. So now I'm ready to anti-differentiate on both sides of this equation. And with the x's, I've got that scalar, so I'm just going to put that 4 in front. Oh, my stylus is not playing nice. Okay, so now I'm just going to anti-differentiate on both sides. So remember, when we have y in the denominator, it's like y in the -1. If we add 1 to the power, then we'd have to divide by 0. This is that special case of the power rule where that is equal to the natural log of the absolute value of y. And again, my constants are all going to be on the right side. So I will apply the power rule over there. So I will have x, so I'll have the 1/2 x squared, which I'll clean up in a second, and then I've got the plus c, which is going to be hanging out over here with the x's. So let's clean that up first. Natural log up. So natural log absolute value of y equals 2x squared plus c. Okay, so anytime that we want to get y equals and it's stuck inside a natural log, just remember that logs are the inverse operation of exponentials. And so this is a log base e. So all I'm going to do is drop some e's in there. So that I have e raised to the power of the natural log of y equals, and I will also have e raised to the power of the right side of the equation. Because e raised to the power of the natural log of something, the e and the natural log just cancel out. And so we've just got the absolute value of y equals e to the power of 2x squared plus c. And then since the y is inside the absolute value bars, we'll just take care of that with a little plus or minus sign over on the right side. So I've got y equals plus or minus e 2x squared plus c. And that is where we will call it a day. Okay. So here on my next slide, I've got dy dx equals e to the 2x minus y. And this one's pretty straightforward if you remember your log properties. Okay, so remember, or not log properties, exponential properties, excuse me. Remember if you have like x to the, let's say 5 minus 2, right? That's the same thing as a quotient, which would just be like x to the 3rd. Okay, but anytime you have subtraction happening in an exponent, it's the same thing as just a quotient. So really here I do have a quotient and I can cross multiply in order to separate my variables. So I can rewrite this as dy dx equals e to the 2x over e to the y. Because now, oh how nice, I can cross multiply. So then I'll have e to the y. Man, you would think I had the handwriting of a toddler. E to the y dy equals e to the 2x dx. I swear I know how to use an iPad. It's just new software. Okay, so we've got e to the y dy equals e to the 2x dx. And now we're just going to anti-differentiate both sides. So remember, don't overcomplicate this. It's just e to the y dy, well, just like e to the x dx, it's just e to the y, okay? And on the other side, because again, my plus c is going to be hanging out with the x's, not the y's. Well, here, I'm just going to have 1/2 e to the 2x. Because remember that if you were to take the derivative of this, you'd have to apply the chain rule. And so you'd have that derivative of 2x is 2 getting multiplied by the 1/2, which causes your coefficient to just go to 1. So we do have to have that 1/2 there. So again, kind of like the previous example, if I've got an exponential and I want to get rid of it, I need a log. Here I need a log with a base of e, which is the natural log. Because again, right, the goal is to have y equals something. Well, my y is in the exponent, so I get rid of that by taking the natural log of both sides, and I get y equals the natural log of 1/2 e to the 2x plus c. And that's it. Okay. Now, we've done several examples with indefinite integrals, so we're going to do just one more example, and then you can stop listening to me complain about my stylus and my iPad. So one more example with an initial value. So in other words, an x and y that we have to plug in so that our answer won't have c. Okay, so let's try that. Okay, so here I have another one that has a nice friendly little quotient to start out with. I've also got my initial condition, which, you know, might also be presented as an ordered pair. Here they kind of wrote it out for us. Okay. So let's start out by cross multiplying. This initial process is the same. I'm going to keep the negative with the x. So I'm going to have y dy equals negative x dx. Okay. So then I anti-differentiate. I'm going to anti-differentiate and not, I'm going to put the negative on the outside. So power rule, here we go. We've got 1/2 y squared. C will be with the x's. So then I'll have equals negative 1/2 x squared plus c. Okay. So I deal with my GCF, and then I'm going to deal with that initial value. Okay, so I'm going to multiply everything by 2 so that I get rid of the 1/2 plus c. Now, it's going to be tempting to be like, oh, but I'm just like one step away from the y. And trust me, it would be okay if you did that, but it's not the fastest way. The fastest way is with this step right here, because I can just square stuff. It's really just simple, right? So I take my initial condition and plug it in. So 2 squared is 4. The negative is outside of the square, okay? Remember, whenever it's written with negative and then x and then squared, you're squaring and then it becomes negative. So this is negative 9 plus c. So c is going to be 13. Okay, so that's my constant. So I will have a specific equation here which is going to satisfy this given initial condition. So then I go back to my y squared here, and I've got y squared equals negative x squared plus 13, because that's c. And then I can take the square root of both sides. So that I've got y equals square root of negative x squared plus 13. And that is going to be my solution. Now, the only thing to keep in mind is that often with these, they're going to come with a domain restriction. Okay, this is one such case because I've got this negative under the radical. Just something to keep in mind is that obviously the domain would have to be such that x squared has to be less than or equal to positive or negative square root of 13 in order for this to not give us an imaginary solution. So the only real solutions, which is what we're talking about when we talk about domain, we just have to kind of keep that in mind that sometimes that's going to come up. But our solution here is going to be y equals square root of negative x squared plus 13, given the initial condition here. And that's it. That is separation of variables.